Hello. In this presentation I'll talk about some joint work with my co-authors listed here. And in this presentation we're interested in studying non-uniform stability for damped hyperbolic PDE models. And a large class of these kinds of PDEs can be studied by considering abstract wave equations of the form shown here. And this equation that we're interested in looks a lot like a second-order ordinary differential equation with variable time t, and the dots here denote the time derivatives of the solution. But this is indeed an abstract differential equation in the sense that the solution is defined on a Hilbert space H. And in this presentation we're interested in what happens to the solutions of the equation as time goes to infinity, and especially we're interested in posing conditions on the parameters L and D in such a way that all solutions decay to zero as t goes to infinity. But let's begin by looking at our equation a little bit in greater detail. And throughout the presentation we assume that H is indeed a Hilbert space and L is a possibly unbounded self-adjoint positive and boundedly invertible operator. And the operator D is assumed to be bounded from some other Hilbert space U into H. And the most important PDE that can be expressed in this abstract form is the n-dimensional wave equation with viscous damping. And this PDE has the form shown here, where delta is the Laplacian, and this equation has a damping term which involves the time derivative of the solution or velocity of the wave profile and some non-negative damping function d. And in order to express this PDE as in this abstract form, we define H to be the L2 space over the spatial domain where the wave equation is defined, and we define L to be the negative Laplacian. And under the suitable assumptions on the spatial domain omega, and with Dirichlet boundary conditions, this is indeed a self-adjoint positive and boundedly invertible operator. And the operator D is defined as a multiplication operator which multiplies a function pointwise with the square root of the damping function. And finally, the initial conditions of the equation also require some conditions, which I'm not going to consider in detail in this presentation, but I'll just mention that under relaxed assumptions, these conditions correspond to mild or weak solutions of the original PDE, and under additional smoothness assumptions we can consider classical solutions of the PDE. Abstract differential equations of this form have been studied in great detail, and there's a lot of theory for their investigation. And in particular, the solutions of and well-posedness of these equations can be studied using so-called strongly continuous semigroups, which are generalizations of the matrix exponential function. And in this presentation we are interested in what happens to the solutions of the equation as t goes to infinity. And in particular we are interested in the convergence of this specific quantity as t goes to infinity for all initial conditions of the equation. And the quantity here involves the norm related to the solution of the equation, as well as the velocity of the solution or the time derivative of the solution. And the motivation for considering this specific quantity instead of just the convergence of the solution is that for a large class of PDEs, this quantity is very closely related to the energy of the solution. And this is especially true in the case of the damped wave equation, where the energy consists of the potential and the kinetic energy. For abstract differential equations, there are different forms of convergence and so-called stability of the differential equation, and we're specifically interested in this so-called non-uniform stability of the equation, which is defined in the form shown here. So here on the left-hand side we have the quantity that we're interested in related to the solution of the equation. On the right-hand side we have a factor which converges to zero with a rate determined by this increasing unbounded function m, and then we have a factor which is only dependent on the initial states of our equation. And the key feature of the non-uniform stability is that this rate of convergence determined by this function m can be quite general, and it in the sense that we can consider very different kinds of functions m, which can either be growing very slowly, in which case the solutions converge very slowly, or converging quite fast. And as I mentioned, there are several different types of stability of abstract differential equations, and non-uniform stability can especially be compared with the most typical form, which is the uniform exponential stability, where all the solutions of the equation decay at a uniform exponential rate for all initial conditions. And non-uniform stability especially appears in damped wave and beam and plate equations in the situations where the damping is either weak in some sense, or it only affects a small subdomain of the spatial domain of the PDE. Especially the non-uniform stability of two-dimensional wave equations with viscous damping have been studied extensively in the literature. And in this particular PDE, the stability depends heavily on the geometry of the spatial domain, as well as the damping region, which is defined as the region or the set where the damping function gets non-zero values. And roughly speaking, if the damping region is relatively large in a suitable sense, then the equation is exponentially stable. And on the other hand, if it's relatively small, then the equation is known to be non-uniformly stable. And these two cases that can be distinguished using the so-called geometric control condition, which tests whether or not all the rays reflecting optically from the boundaries of the spatial domain meet the damping region, or alternatively fail to do so. And in the case where this condition fails, we indeed always get non-uniform stability, and this mainly just illustrates that non-uniform stability is quite a typical form of stability for damped wave equations. Our intention is to introduce some general conditions, especially on the operators L and D, which can be used in testing and proving non-uniform stability. And as I said, non-uniform stability has been studied actively in the literature for wave equations and many other types of PDEs, but there's still a lot of things that need to be done on a case-by-case basis. And what our research aims at is to just introduce new and fairly general tools which can be used in verifying that a model PDE system is non-uniformly stable, and in identifying the decay rate for the solutions of the equation. What we are specifically interested in are so-called observability-type conditions relating the operators L and D. And this kind of an approach is not something that we arrived at by accident, but instead there's a long history in studying the relationship between observability properties relating L and D and the stability of this abstract differential equation. And especially a suitable type of exact observability is known to be equivalent to exponential stability of the equation, and similar results hold for weaker forms of observability and stability. And in our research, we are introducing conditions which can be seen as generalized forms of observability, and we relate these to the non-uniform stability of our equation. And in the next part I will introduce my main results, and here I'm focusing on just two specific results from our research on this topic. And the first result involves a observability type condition shown here. So this is a parameterized inequality involving a scalar parameter S and the operators L and D. And in addition, it involves two non-decreasing and possibly unbounded functions M0. The form of this inequality is indeed familiar from classical study of observability, where it's known as this kind of a Hautus test type condition, which is often used in testing observability of a pair of operators. The reason why this is a generalized concept is that we allow these two parameters M0 to be in general unbounded functions, and when these are growing we arrive at a generalized form of observability. And our main result on this particular condition is that if L and D are such that this condition holds, then our equation is indeed non-uniformly stable, and we in addition get an explicit rate of convergence for the solutions of our equation. And the way we get this convergence rate is that we define this function capital N, which involves the product of the functions M0, which appear in the observability condition, as well as an additional quadratic term. And then after this, the rate of decay of the solutions is determined by the algebraic inverse of this increasing function. And because the rates of growth of the function n and its inverse are closely related, we can also deduce that if the function n and especially the parameters m0 grow relatively slowly, then the algebraic inverse grows relatively fast, which means that the decay of the solutions is relatively fast. And especially if n is bounded by a polynomial, then the solutions decay at a rational rate. And on the other hand, if n grows very quickly, for example at an exponential rate, correspondingly the solutions may decay at very slow rates, for example logarithmically. And the second result is based on a condition which involves the spectral projections of the positive operator, which is the square root of L. And I'm using the square root here just in order to keep the the formula is fairly simple, but of course the spectral projections are closely related to the spectral projections of the operator L itself. And this condition that we're interested in is involves the lower boundedness of the operator D, a joint of D, when we restrict this operator onto the spectral subspaces of the square root of L. And the way we do this is that we take a parameter S from the positive real axis, and then we take a spectral interval centered around S with a radius delta, which is allowed to depend on S. And then we indeed restrict our joint of D onto this corresponding spectral subspace, and we test whether or not this operator or its restriction is lower bounded with a bound gamma, again something that's allowed to depend on the point S. And if this is satisfied for all S, then we say that the operators L and D satisfy this so-called Wavepacket condition. And in this condition, these delta, the radii of the spectral intervals, as well as the lower bounds, gamma depending on S, may in general be non-increasing and also typically decreasing functions of the parameter S. And our main result involving the Wavepacket condition is that if L and D are such that this indeed holds for some functions gamma and delta, then our abstract differential equation is non-uniformly stable. And moreover, we can again deduce a rate of decay for the solutions of this equation. And this time the function capital N is determined by the functions gamma and delta. And if we assume that it satisfies an additional condition guaranteeing that it doesn't grow too slowly, then the decay rate is again determined by the algebraic inverse of this function capital N. So these results are taken from our paper, which was recently accepted, and in the actual paper we have several other results involving especially several alternative types of observability conditions. And in addition, we also investigated similar results for first order abstract differential equations. And finally, we also deal with a case which is theoretically quite challenging, where the operator D is allowed to be an unbounded operator. And such operators especially facilitate the study of non-uniform stability for wave equations which are damped on the boundary of the spatial domain. And finally, to conclude, I want to talk about what our results say about specific PDE models. And as I said, in the case of the wave equation with viscous damping, non-uniform stability has been studied actively in the literature, and our results in particular reproduce certain stability results which are already known in the literature. And to be fair, many of these results have already been using similar approach of observability-type conditions and also employed these abstract methods. But our results also generalize these known stability results, and there are also some more recent research which specifically aim at deriving these generalized observability-type estimates for the wave equation, but which have not yet been connected to the stability properties of the equations. And in such situations, our results can be used as a bridge to link these newly derived observability estimates to the stability properties of the wave equation itself. And the two-dimensional wave equations are also a good test case to consider the optimality of our general results. And fairly recently in the literature, it's been observed that certain types of additional smoothness conditions on the damping function d can radically improve the stability properties and decay rate of the equation. But on the other hand, in many cases, such smoothness conditions are invisible to the observability conditions that we've considered in our research. And because of this, there's a certain inherent suboptimality when it comes to applying our results to the two-dimensional wave equation. And in addition, we can of course apply our results for one-dimensional wave equations. And in this situation, viscous damping always leads to exponential stability, but there are also other forms of damping. And especially this kind of a non-local average type of damping can be studied very conveniently using our Wavepacket condition. And this way we can convert the investigation of the non-uniform stability of this equation into the study of the Fourier coefficients of the damping function d. And in this situation, our results produce the optimal degree of non-uniform stability and rates of decay, and this we have shown in our paper as well. And finally, in a recent work cited here, the authors used our results in order to investigate the stability properties of a so-called water wave system, which is a two-dimensional coupled PDE system modeling the dynamics of small amplitude water waves. And in this article, the authors were actually considering a control situation where they have a boundary control affecting a part of the boundary of the system, and they were using our results to design a control law which achieves non-uniform stability for the controlled equation. And they were especially using a Wavepacket condition in our results. So this concludes my talk, where I've introduced some new results on testing and proving non-uniform stability for abstract damped wave equations. So thank you very much for listening, and if you have any questions, please feel free to contact me. Thank you.